hypothesis test for a difference between two means. And the example today is something called the stroke stent study, where researchers randomly assigned stroke patients to two groups, one receiving the current standard of care, which is the control group, and the other receiving a stent surgery in addition to the stent. And this gentleman, Dr. Jeffrey Saber, was a principal researcher for the study. Okay. So right away, we can see the 10, I mean, I look at this and I say, okay, 10% condition, it's an experiment. And they were randomly assigned. So I've already thought in my head, I've met two of the three conditions. Okay. So here's the study results for our sample. Okay. So if the stents work, the treatment group should have a lower average disability score. Okay. So just keep in mind in this example, lower is better. Higher is worse. So we see just by looking at these results alone, like just by looking at the mean disability scores, we see the stent group had a lower average disability score. So that suggests, yeah, that seems to be better than just standard care. But once again, we don't know if this just happened by chance alone, that if we did another two groups, that this one would be bigger than this one. We just don't know yet. More analysis is needed. So we're going to do a hypothesis test. So the null hypothesis is going to be the current standard of care is the best. In other words, there's no difference between the current standard of care, the control group, and the stent group. So we would say that, we could say it one of two ways. The average disability score for the stent group is going to be the same as the control group. So that means that the stent group didn't have a positive impact. Or if we take the average of the stent group, the average disability score, subtract the average disability score, it's nothing. There's no difference. Either one of those is correct. If the stent is better, and the average score is going to be less than, for the stent group, is going to be less than that for the control group. Or if I take the average of the stent group minus the average of the control group, it's a negative value. Remember, lower is better with disability score. So this represents the first stage of a hypothesis test. And remember, you do have to define your variables. So we have to define these two. And remember, it's not X bar, so it's the true mean average. I'll just put ABG, disability score for the stent group. And this one, I can just do ditto, true mean average disability score for the control group. And remember, the goal of the hypothesis test is we want to find the p-value, the probability of our sample being less than, or the difference in our sample being less from stent to control, or if I subtract the two, I get less than 0. Okay, so long way. It's good for you. Builds character. Okay. So in a world where the null hypothesis is true, stents do not lower average disability, how likely is the data we have gathered? So that's calculating the p-value. So we need to look at the sampling distribution. And then from that sampling distribution, we need to find the number of standard errors our sample is away from the mean, and then we need to find the probability of getting that. So notice this is basically the same as what we did yesterday when we did the confidence interval for two means. I don't know if you recall, but when we did proportions, we had to calculate a new proportion, the combined proportion. We don't have to do that for means. So in our example, and remember when we're dealing with means, it's not normal, it's t. Well, we always, with a hypothesis test, we always go with our null hypothesis for this value. So the average of our sample stent minus our sample control is 0, because that's the null value. And our standard error, we're going to calculate it the same way we did for a confidence interval. And that's by taking the standard deviation of the stent group squared divide the number of people in the stent group plus, never minus, the standard deviation of the control group squared divide how many were in the control group sample. Just to remind you, that's the null value that we see. Okay, so already got this value, so we don't have to calculate it. But we do have to calculate the standard error. By doing the square root of the standard deviation of the stent group, which was 1.78 squared, divided by how many were in the stent group. And so from the first page table, that was 98, plus the standard deviation of the control group, which was 1. Yeah, same thing. 1.78 squared over the sample size of the control group, which is different at 93. And I'll just, so if we do that calculation, we're going to get approximately 2.58 for our standard error. So what does all that mean? Well, remember, here's our t distribution. So this represents the mean point estimate, which is the null value, 0. And then we add the number of standard errors and subtract the number of standard errors. So this would be 2.58. This would be, sorry. Oh, wait. I got two different values. I got to do this again. Because I got 2.58 and 0.258. I think I may have done it wrong. 1.78 squared divide 98.
plus 1.78 squared divide 93. No, it's, sorry, I gave you the wrong.
Type that in correctly. It should be 0.258. 0.258. So 0.258, 0.516, 0.774 when I add 0.258 three times. Start at 0 and subtract 0.258, so I get negative 0.258, negative 0.516, negative 0.774, and notice I made room for some standard errors, probably tells you where the p-value is going to go. Okay. And so remember, this is our distribution of sample differences. So it would be that's what you could label it. Okay. It's the difference in disability scores, stent group minus control group. So now we have to figure out where is R value? Okay, how many standard deviations away is, or standard errors away is R value? So in a world where stents and standard care are equally effective, mean of 0, would our study results be unusual? So we have to calculate and interpret the t-test statistic and the p-value. And then we can put that on the t-distribution diagram. Okay, so remember when we did, this all goes back to Unit 2 when we did a Z-score. And remember, a Z-score it's all based on this formula. Was the data value minus the mean over the standard deviation. Okay. But remember, we're calculating a t-score for this one because it's a mean. Okay. And our data value is going to be the difference we got in our sample. So it's going to be the difference in our, how do I say this? The average stent disability score minus the average control disability score. And then we're going to subtract that by the mean, which up here is 0. Okay. So it's what we got under our null hypothesis. Wait. This is what we assume to be true, what we assume to be true of the population. Divided by the standard deviation, but remember we called it the standard error of the difference in the sample. So the difference that we got in our sample, if you go back to the first page, it's 2.26 minus 3.23. Those are the average disability scores we got from each group. Minus the mean, which is 0, over the standard deviation or standard error, which we calculated already to be 0.258. And when you do that, you get approximately negative 3.76. Well, the negative just means it's 3.76 standard errors below. That's quite a distance. Okay, 3.76 of them. Like here's one of them here's 2 of them, here's 3 of them, so we're way out here. So we can see that that p-value is going to be low. Okay? So to calculate the p-value, this is where we do a normal distribution calculation, but because we're dealing with means, it's a t-distribution calculation. So we're going to do t-CDF. And when you bring up that, it's going to ask for the lower. And remember, we're working on this side, so the lower is going to be negative 1,000. The upper is going to be negative 3.76. And the degrees of freedom, if you remember from yesterday, to find the degrees of freedom, we take the sample size minus 1. But if there's 2 samples, take the lower one. Okay? So it's going to be, the lower sample was 93 in the control group, so it's going to be 93 minus 1 equals 92. Okay? And that's the lower sample size. So when we calculate all of that, it's going to give us 0.0001. This should tell you something right there. Yeah. Yes, because here, I'll show you. Because remember, so if we go back to the diagram, if I continue on with, so what was the difference between, what was our sample? It was this minus this, which was negative, so it was 2.26 minus 3.28, right? Which works out to negative 0.97. Well, negative 0.97, if you look, we're going into the negatives, it's going to be somewhere around here. Somewhere around here. So which means I want to find that area, right? Okay. So to find that area, the lower is going to be negative 1,000. The upper is going to be how many standard errors away.
Why do I feel like I have that wrong? Why do I feel like I don't have that right? Should it be? No, it should be negative. Why am I doubting myself? TCDF lower is negative 1,000. Degrees of freedom is 92. Decimal places. Why wouldn't it?
I got it. Because it's a different label plot. Like, remember, this shows us the standard error in our sample. It doesn't show us the number of standard deviations away. Okay? Remember, the number of standard errors, we would do one like this. A standardized t-distribution. So it would look like this, and I'm trying to figure out negative 3.97 that way. I got it. I got it. Yeah.
So what do we erase? So what was wrong?
We erase nothing.
What? What's where at?
We erase, everything's fine. We erase nothing. No, I was questioning myself, but I was putting two values on, that should be on separate distributions. That's a mistake that I made. Okay, anyway, here's our P value. That's what we want to hone in on. That's really low. Remember, what's the standard significance level, or what's the significance level that we normally use? 0.05 or 5%. Okay, so under the assumption that stents provide no added benefit, the actually observed data, a 0.97 decline in disability score, is highly unlikely because the p-value is so low. So I reject my earlier assumption, or the null hypothesis. There is convincing evidence that the stents lower the disability score. Now, we're not. Okay. We saw how we can actually calculate the t statistic, and from that get the p-value. Okay. But now we're going to do the graphing calculator function that does it all for us. But still, we have to set up a proper solution using form components. So we are going to state. And remember, this is where we just state the null, the alternative, and what the variables represent. So this goes back from the first page, where we can say the difference in the average stent disability score minus the average control group disability score is nothing. No change. The alternative that we're trying to prove, that difference is actually less than 0. If I take the stent average minus the controlled average, I'll get a negative value, which means the stent works. And then remember, we have to define these just like we did here. It's true, mean, disability score. For the stent group, true, mean, disability score for the control group. how we're doing this, what the plan is. We are going to perform a two-sample, and because it's being t-test for the true mean disability score percent minus the true mean disability score for the control group. If random 10%, and what was the last one? For means? Large sample. What was it per proportion? Right. So random, groups were randomly assigned, said that right at the beginning. %. Experiments. Don't need to verify. And then the large counts. Large sample, is the first group sample size greater than or equal to 30? Yes, because what was it, 98? So first group that was 98 greater than or equal to 30. For the second group, it was 93, which is greater than or equal to 30. Therefore, we can continue. And now we continue with the graphing calculator. So the do phase, here's how we do it. Okay. What are we doing this time? Two sample t-test. So when you pull that one up on the calculator, sample t-test is number 4. We want to highlight stats, and then you're going to be asked for similar values that we did when we did a confidence interval for difference between two means. So the average of our first group sample was 2.26, the disability score, and its standard deviation was 1.78, and the sample size was 98. So that's all the stent group. And then for the control group, which is the second group, its mean disability score was 3.23 in the sample. The standard deviation of that one was also 1.78, but the sample size was a little bit smaller. At 93, remember we are testing this. And is it pooled? No. Pooled only applies when we do difference between two proportions. So pooled, no, because we didn't combine the standard deviations. So when you do all of that, I'll enter it. So 2.26, 1.78, 98, 3.23, 1.78, 93. We are looking for less than, and it is not pooled. So we are asked to calculate it, and then you see, we get that t-score when we did it the long way, negative 3.76, but we're focused on the p. Okay, 1.11, et cetera, times 10 to the negative 4, which is the same as 0.301, which is the p-value we got when we did it alone. So the p-value was approximately 0.001.
If you wrote it like the one that if I said.
And that's fine. That's fine. And finally, we conclude because our p-value is less than our assumed alpha value of 0.05. Remember, if it doesn't give you a significance level or an alpha level, just assume it's 0.05. We reject HL. We have convincing evidence. And then really, to find what the rest that you write, you just go back to the question. Because it says, do the results give convincing evidence? Oh, it does say there's significance level in this one. The stent treatment reduces the average disability stroke. So I'm just going to rewrite that. We have convincing evidence, the stent treatment. Reduces the average disability from stroke. All right, we made it through all 8 confidence intervals and hypothesis tests. Okay. Okay,